Okay, now let's solve the problem 49 that is related to the uh, relative motion. Now, a bolt drops from the ceiling of the moving train car that is accelerating northward at the rate of 2.5 meter per second squared. In part A, we have to find what is acceleration of the bolt relative to the train car. In B part, what is the acceleration of the bolt relative to the Earth? Describe the trajectory of the bolt as seen by an observer inside the train car, and D. Describe the trajectory of the bolt as seen by an observer fixed on the Earth. Now, let's draw the picture. Now, we know that if you draw a coordinate system, positive y, this x, and this is north. Okay. Now, our bolt is so basically the train is moving with an acceleration, right? So we call this one acceleration of the train car. Let's just say car, okay? Acceleration of the car relative to the Earth, which is given as a 2.5 meter per second square. Okay, this is acceleration of the car relative to the Earth. Then we have here our bolt. So then we have acceleration of the bolt relative to the Earth, okay, which is actually the value of the G. Now, when it's released from the rest, we will see that we're going to have this acceleration. Okay, now this acceleration can be found by using Pythagorean theorem, which is acceleration of the bolt relative to the car. Okay, acceleration of the bolt relative to the car is equal to ACE squared plus acceleration of the bolt relative to the Earth squared. Now let's plug the numbers. Acceleration of the car relative to the Earth is 2.5 squared plus 9.8 squared. If you do calculation, you will find that it's equal to 10.1 meter per second squared. Okay. Now, if that's the case, then you can also find the angle. Let's say you want to find this angle. Okay. Now, if you want to find this angle, the theta is equal to inverse tangent ACE, acceleration of the car relative to the Earth, divided acceleration of the bolt relative to the Earth. So you plug the numbers and you should find that it's equal to 14.3 degrees. Okay. We can also represent this acceleration of the bolt relative to the car in terms of ACE I vector plus ABE J vector. Okay, so that means in the part A, we can say that acceleration of the bolt relative to the train car, acceleration of the bolt relative to the train car in terms of the I vector, we can say that it's equal to negative 2.5 meter per second squared. Okay, or you can say that it's equal to 2.5 meter per second squared, but it's moving to the south. Okay, now what about in B part? In B part, what is the acceleration of the bolt relative to the Earth? Now again, acceleration of the bolt relative to the Earth, we can say that it is equal to the G, which is 9.8 meter per second squared. Okay, it's pointing downwards. Then describe the trajectory of the bolt as seen by observer inside the train car. Suppose if the person is standing, okay, if person is standing inside the train, then he's stationary. So therefore he will see that the trajectory or the bolt will just fall down with downward gravitation, okay, which is 9.8. But however, now if observer is standing on the earth, okay, if the person is standing on the earth, then he will see that bolt, if it's released from the rest, then it will be moving parabolic, okay. Now why it's moving parabolic? Why? Because the bolt is actually moving with a speed, okay. Why? Because it's inside the car. Since it's having initial velocity, and also due to the gravitational force G, our object will move parabolic, okay, with respect to the vertical axis.